the theorem from the last lecture, which showed that given any polynomial non-constant over a field, there exists some extension field where that polynomial has a root, motivates us to see how far we can take this process. Let's just do some exploration here. So let's let f be a field. Little f belong to the polynomial ring over the field f. Now, by theorem 157, there exists a field extension phi going from f to e, in which phi bar of f has a root. Well, that means that we can write phi bar of f. Let me say that it has a root a. That means that we can write phi bar of f as some x minus a times g inside e adjoint x. So we can factor this because any root corresponds to a linear factor of the form x minus that root when you're working over a field. Now, if g is a non-constant polynomial, we can repeat this process. So I want to I want to repeat this, so I'll say that we actually have phi 1 going from f to e1, in which phi bar of f has a root a1. So phi 1 bar of f is equal to x minus a1 times g1 inside e adjoint x. So now, if the degree of g1 is greater than or equal to 1, that is, if g1 is non-constant, we have that there exists phi 2 going from e1 to e2, again by theorem 157, just repeating it again, such that phi 2 bar of g1 is equal to x minus a2 times g2 inside the extension field e2 of x. And we can continue doing this over and over again. So we can repeat this until we get a gn with the degree of gn equal to 1. And we know that this is the case because g1 will have degree 1 less than the degree of f, g2 will have degree 1 less than the degree of g1, and so forth and so on. Every time we go through this process, the degree of the g component here is dropping by 1. Now, this means that if we move all of this into the field En, the final field that we get here, we can get that we can let phi be phi n composed with phi n minus 1 composed down to phi 2 composed to phi 1. And so now phi bar of f, which is going to lie in the polynomial ring over En, this is going to equal x minus a1 times x minus a2, etc., times x minus an times gn inside enx. And technically, I need to I need to write down, instead of A1, this is going to be the image of A1 when we apply phi2, phi3, etc. up to phi n. So I'll just call it A1 bar, A2 bar, etc. up to AN. Now this AN actually does belong to EN originally, where this GN here is a constant. And it's going to be a non-zero constant because we started with a non-zero polynomial f. And all of these ring homomorphisms are injective. So this suggests, this proves really that given any polynomial and any non-constant polynomial over a field, there's some field extension where the polynomial doesn't just have a root, it has as many roots as possible, where it factors completely into linear factors. And that sort of field is what we want to look at. It's what we are going to call a splitting field. So let's go to a definition, and then we'll prove some things about splitting fields. So definition 159. Let's let phi from F to E be a field extension. Now, some preliminaries. Given a set A, a subset of E, the smallest subfield of E containing A is denoted containing A, and the image of F is denoted F of A. So it's the smallest field inside E, which contains both the image of the field F and a bunch of elements, a bunch of additional elements that we choose. Now, most of the time we're dealing with finite sets, so if this A does happen to be a finite set A1 through AN, we may write F of A1, A2, and or the minimal extension field of F containing A1 through AN for F of A. So the smallest field containing both F and, or the image of F and all of these elements A1 through AN. Now, if F is a polynomial with coefficients in the field F, with the degree of F greater than or equal to 1, we say that F splits in E if there exist A1 through AN in E, or A and A1, A, comma, A1, A2, etc. up to AN in E, such that phi bar of F is equal to A times x minus A1 times x minus A2, etc., times x minus AN inside the polynomial rings over E. Note that this implies that A actually belongs to F, because the leading coefficient of this polynomial will be A, and because F, the leading coefficient of F, has to be from the field F. Now, so this is what it means for F to split in E. Now, we want to say something more. If, in addition, we have that E is the smallest field containing the image of f, the field f, and all the roots of the polynomial f, then we say that E is a splitting field for the polynomial f over the field f, and we say that this field extension phi realizes the splitting. Now, this last term, phi realizing the splitting, this is not. This is my term. This is not the generally accepted term. As far as I know, there is no general term for this here. However, everything else here is very standard, very conventional. So we can think of the splitting field as being of a polynomial as being the smallest field in which the polynomial splits into linear factors. The smallest field in which you can factor the polynomial completely into linear factors. Now, the first theorem has to do with the existence of splitting fields. And in fact, we've pretty much already proved it. Theorem 160 says, given a field f and polynomial little f inside the polynomial ring over the field f, there exists a splitting field for f over the field f. Now the proof, this was the first slide. The first thing we did, putting it into a perfectly rigorous form would require a tiny bit more exposition, but all the ideas are there on the first thing, where we basically just apply theorem 157 over and over and over and over again. Or if you want to think about it another way, we take the polynomial f, we factor it as much as possible, and then any factors it has that aren't linear, we move up to a bigger field where we can factor out a linear form, and then if we're done, great. If not, we keep doing that. We just keep moving to bigger and bigger extension fields until we're done. Now, the one thing that's left is to show that a splitting field exists within the fields that we created. So based on the arguments of the first slide, we will have constructed a field in which f splits. So the field that we've created will be one in which f splits, but we haven't yet shown that it is a splitting field for it because it might be too big. So the only thing that we need to do is to show that given a field extension phi from f to e and elements a1 through an in E, the only thing that we need to show is that the field f of a1, a2 up to an subset of E exists. So when we defined this notation, we said that it's the smallest field containing the image of f and all the elements a1 through an. There's a little bit of argument needed to show that such a thing exists. But it turns out that you can do this proving this is an exercise, and it comes down to showing that if you take all of the subfields of E, which contain F and the elements A1 through AN, and intersect all of them, then you get this that you're looking for. That's the basic idea behind it. So that's the only thing that was left to do to match the definition in order to prove Theorem 160. So let's see an example. So if we look at the polynomial f x squared plus 1 sitting inside the polynomial ring over the real numbers, this splits in the complex numbers, since in C adjoin x, we have that f is equal to x squared plus 1, which is x plus I times x minus I. So in C adjoin x, we can factor f into linear factors, which means that f splits in C. Now, also, we have that C is a splitting field for f over the real numbers, since well, what we have to do basically is show that if we look for the smallest field inside the complex numbers, which contains both the real numbers and the roots of f, so that'd be r of I and negative I, this must contain a plus bi for all a and b in the real numbers. It has to be a field, and so it has to be closed under addition and multiplication, and so and it has to contain I, which means that it has to contain I, it has to contain bi, and it has to contain a plus bi for any a and b in R, which this has to contain. So this means that R of I and negative I is in fact equal to all of C. Now, let's be careful here, because C is not the splitting field for x squared plus 1 over q. The splitting field for x squared plus 1 over q will be q of I negative I, which will be the set of all a plus bi, where a and b are rational numbers. It turns out that this is a field, and it's therefore the smallest field, which contains both q and I, and therefore negative I as well. But in particular, this is a proper subset of C. So when describing whether a field is a splitting field of some polynomial, you need to specify what ring the polynomial belonged to originally. Did it belong to a polynomial ring with coefficients in, for instance, the real numbers, or in the rational numbers, because that makes a difference when we talk about the splitting fields. So the splitting field for x squared plus 1 over r is the complex numbers, but the splitting field for x squared plus 1 over the rational numbers is not the whole set of complex numbers. It's a subset of those with rational coefficients. All right. So we saw in Theorem 157 how we can build a splitting field of an irreducible polynomial. Sorry, we can build a field which contains a root of an irreducible polynomial. But we could also have a root of that polynomial sitting inside some other random field. And it turns out there's a relationship between those. Now, Theorem 161 is is important. So let's let f be a field. Little f inside the polynomial ring over the field f, an irreducible polynomial phi from f to e, just any field extension, and a in e, a root of f. So phi going from f to e is a field extension containing some root of f. Or sorry, a root of phi bar of f, to be precise. So if this is the case, then we have two different fields that we can construct which contain a root of f, or a root of phi bar of f under their respective phis. On the one hand, we have f of a. So we just take the smallest subfield of E, which contains this root E, this root A of f. But we could also, from Theorem 157, construct this field, f adjoin y, modulo f of y, where here f of y is just what we get by taking the polynomial f and replacing all of its coefficients with all of its variables x's with y's. And in fact, these are isomorphic. No matter what e we start with, the two ways of constructing the smallest field containing a root of little f give you the same thing. So these are isomorphic as f extension fields. All right. Furthermore, we can say more. Furthermore, a basis for f of a as an f vector space is given by 1 a squared, etc., a to the n minus 1, where n is the degree of f. So we can say a lot of things here. If we take our field f and put in any root of little f, take the smallest field containing all that, it can be described very specifically. We can describe its basis. In particular, we can say from this that it's an n-dimensional f vector space, where n is the degree of f, and we've got this isomorphism of extension fields that we can work with. All right, so let's see how this works. We want to show an isomorphism of f extension fields, and so we're going to use the first isomorphism theorem to do this. So let's let phi from f adjoin y to f of a be given by psi of g equals phi bar of g of a. So this function takes a polynomial over f with variable y. It moves it to e adjoin y by replacing each coefficient with its image under phi, and then replaces all the y's with the element a. Now, since a is a root of phi bar of f, we have that psi of f of y is equal to phi bar of f of a, which is equal to 0. And so we have that f of y is in the kernel of psi. Therefore, the ideal generated by f of y is a subset of the kernel of psi. Now, let me go up. Now, since f of y is, the ideal generated by f of y is maximal in f adjoin y, we proved this for theorem 156, I believe. So since this is maximal in f adjoin y, and since phi of 1 psi of 1 equals 1, which is not equal to 0, we have that the kernel of psi has to equal the ideal generated by f of y, because it has to either be this ideal or the whole ring, and it's not the whole ring. So the kernel of psi is the ideal generated by f of y. So that means that f of y mod, or f adjoin y mod the ideal generated by little f of y, is isomorphic to the image of psi by the first isomorphism theorem. Furthermore, we have that the image of psi is a field. And because it's isomorphic to a field, and it contains phi of f and a. Since psi of y, of just y, is equal to a, and psi of x is equal to phi of x for an let me not do x there. Psi of z is equal to phi of z for any z elements of f. So this is a field which contains phi of f and a, and since f adjoin f of a is the smallest field inside E, which contains both of these things, we must have that f adjoin a is contained in the image of psi. But by definition, we had that psi only went into f of a, and so we have that f of a is equal to the image of psi. Therefore, psi is an isomorphism. And that proves the first part of the statement. The last part, talking about a1, a squared, etc., being a basis for f of a, follows from the fact that 1 bar, y squared bar, up to yn minus 1 bar is a basis for f adjoin y over f of y. And this part is an exercise. All right, so this tells us that we can describe the smallest fields that contain a given root of an irreducible polynomial in a standard way. In particular, one of the things this means is that if I take two different roots of an irreducible polynomial and look at the smallest fields containing each of those, they're going to be isomorphic because each of them are isomorphic to this one field, which doesn't depend on a particular root of f at all. And so from the point of view of field extensions, all roots of an irreducible polynomial are sort of interchangeable, and we're going to make that much more precise later on. All right, so let's look at an example. So let's let f be the polynomial x to the sixth minus 2 inside q adjoin x. Now, I can point out two different roots of f inside the complex numbers. So both the sixth root of 2, the real number sixth root of 2, and the sixth root of 2 times 1/2 plus the square root of 3 over 2i are roots of f in C. Theorem, it turns out that x squared minus 2 is irreducible in Q. Quick exercise, why is that? So theorem 161 shows that if I take q adjoin the sixth root of 2, so this is the smallest subfield of the real numbers, which contains both the rational numbers and the sixth root of 2. This is going to be isomorphic as q extension fields to q of sixth root of 2 times 1/2 plus the square root of 3 over 2i, which is a subfield of the complex numbers, the smallest subfield of the complex numbers, containing both the rational numbers and this particular complex number, root 6 of 2 times 1/2 plus 1 square root of 3 over 2i. Furthermore, based on the basis construction, we have that the field q of sixth root of 2 can be described as a plus b times the sixth root of 2 plus c times the sixth root of 4 plus d times the sixth root of 8 plus e times the sixth root of 16 plus g times the sixth root of 32 for some a, b, c, d, e, and g rational. And furthermore, these constructions are unique. These a, b, c, d, e, g are unique. So as q vector spaces, q of the sixth root of 2 is isomorphic to just q6. Now, these are isomorphic as q vector spaces. They are not isomorphic as q extension fields. So remember the point that we made a little while ago, that when we write down an isomorphism of two things, we have to be careful when we say, well, an isomorphism as what? These are isomorphic as q vector spaces, not as anything stronger. But it does mean that every element of this set can be written uniquely using a 6x1 vector of rational numbers. All right, so the big result we have in this section so far is that splitting fields exist. Given any polynomial, we can always construct a splitting field of it. The next result, which Theorem 161 gets us closer to, is that splitting fields are unique up to isomorphism. We're going to be able to talk about the splitting field of a polynomial, and that's going to make sense if we consider two fields the same if they're isomorphic as F extension fields. So let's see how this goes. Now this proof takes a little bit of work, more work than the other ones that we've done so far. So let's get into it. Theorem 162. Let F be a field, and F inside f of x a non-constant polynomial. Any two splitting fields of F are isomorphic as F extension fields. All right, so let's see how this goes. We're going to work by induction. We proceed by induction on the degree of F. Now, if the degree of F is equal to 1, then F itself is linear. Then that means that the field F is already a splitting field for F. So for any field extension B from F to E, realizing a splitting we must have that E equals phi of F, since E is the smallest subfield of itself in which F splits, in which phi of F splits. So in particular, this means that phi is an isomorphism. And so F is isomorphic to E. So the base case says that any splitting field of a degree 1 polynomial has to be isomorphic to the field that you started with. All right, so now let's move on to the inductive step. So now let's let the degree of F be greater than or equal to 2. And suppose we know the result for smaller degrees. So let's let E be a splitting, any splitting field of F over field F, and be a field extension realizing the splitting. Let's let G be an irreducible factor of f in the polynomial ring over the field f, and an element A inside the splitting field, a root of G. So now let's let f prime be this field f join y of modulo the ideal generated by G of y. So that, as we just proved in the previous theorem, f prime is going to be isomorphic to f of A. So the minimum, the smallest subfield of E containing both the image of the field f and the element A. And furthermore, we want to specify what this isomorphism looks like based on what we did in the last theorem. So the isomorphism psi, going from f prime to f of A, is given by psi of h of y, h of y bar, because that belongs to the quotient field, the quotient ring f prime. This equals phi bar of h of A. Now here we've got that h is a polynomial belonging to f adjoin x, which means that h of y is a polynomial belonging to f of y, where we just replace the x's with the y's. And so h of y bar, this is h of y plus the ideal generated by G of y, and this belongs to f prime. So just following through where all these elements live. Now, since y in f prime, y bar in f prime is a root of f bar, where f bar is what we get when we move from the polynomial ring f adjoin x to the polynomial ring f prime adjoin x. So this is just following what we've previously done. We have that f bar is equal to x minus y bar times j, for some j belonging to f bar adjoin x. So y bar is a root of G, and since G is a factor of f, it's a factor of f, so or a root of y bar is a root of f bar, and so we can write f bar factors this way. Now, we claim that phi bar from f bar to E is a field extension realizing a splitting of J. So let's see how that goes. So first of all, note that phi is injective, since it's a bijection with image a subset of E. So phi from f, psi from f prime to E is injective, so that's the first thing. So now to recognize that psi is a splitting of j, we're going to go back through what we know about f. So let's let f be the sum of ai's times x to the I. So then we have that psi bar of f bar is equal to psi bar of the sum over I of ai bar xi, where this ai bar is the element of f prime with representative ai. Now, psi bar is a ring homomorphism, so that means that we can bring it inside. And in fact, the definition of psi bar means that we will turn it into psi of ai times x to the I. Now, when we take psi of ai, remember that we had that psi of a polynomial is that polynomial evaluated at a after applying phi to it. So phi of that polynomial evaluated at a. So this is by definition phi of this polynomial evaluated at a, but this is a constant polynomial. So this is just phi of ai times x to the I, which is by definition phi bar of f. So what we've done here is we've essentially created a couple of diagrams like we were doing before. So we have f going from sorry, let me make this clearer. So we have phi going from f to e. Sorry, I had that right the first time. Phi going from little f to e, and then we also have that this f is going to f prime. This is basically just by the inclusion. So this is the over bar notation that we've been using here. And then f prime is going to e by this homomorphism psi, and this psi is constructed in such a way that this diagram commutes. So again, if I start at f and I go to e either by phi or by moving to f prime and then applying psi, I get to the same thing. Now, if we apply things on the level of polynomial rings, we've got f adjoin x, which goes to f prime adjoin x, and we're using the same notation of the bar for this part. Now f adjoin x goes to e adjoin x. That function is phi bar that we're using, and we've got psi bar. And what we are showing, or what we've just shown using this computation, is that this diagram commutes as well. So on the level of polynomials, we have this commutative diagram where going from f adjoin x to f prime to e adjoin x is the same thing as just going directly via phi bar. Now, the reason why this is relevant is that we now have that phi bar of f splits in E. So that means that phi bar of f bar splits in E. But we also have that phi bar of f bar is equal to phi bar of x minus y bar times j, which is actually x minus a times phi bar of j. So we have that phi bar of f bar splits in E, which means that this product splits in E, so that means that phi bar of J splits in E. Furthermore, every root of phi bar of F other than A is a root of phi bar of J. It has to be, because all the roots of phi bar of F have to show up somewhere in here. And if it isn't A, then it has to be a root of phi bar of J. So that means that since E is the smallest subfield of itself, containing all the roots of phi bar of F, it is the smallest, or containing phi of F and all roots of phi bar of F. It is also the smallest containing F of A, so containing A and all the roots of psi bar of J. So E is the smallest subfield containing both F of A and all the roots of psi bar of J. But now we know that F of A is equal to the image of psi. That's how we constructed it. So that means that E is the smallest subfield of itself, containing the image of psi, or let me write it differently, as psi of F bar and all the roots of psi bar of J. Thus, E is a splitting field. Of J. And J, just by way of reminder, belongs to the polynomial ring over F prime. Okay, so we've shown that any polynomial ring, any splitting field of the polynomial F is also a splitting field of this polynomial J that sits inside this ring F prime of X. So now let's let E prime be any other splitting field of F. So by the same argument, E prime is a splitting field of J over F prime. Now we have that the degree of J is equal to the degree of F minus 1, because we had that F bar is equal to X minus Y bar times J. So by induction, this means that E and E prime are isomorphic as F prime extension fields. Thus, since F is a subset of F prime, we have that E is isomorphic to E prime as F extension fields. And this is an easy exercise. Okay, so we were able to show that splitting fields are unique up to isomorphism by induction, saying that if you are the splitting field of a polynomial, well, then you're a splitting field over a factor of that polynomial over a slightly larger field. And therefore, we can use induction to move things down. So all splitting fields of a polynomial over a given field are isomorphic, which means that we can talk about the splitting field of a polynomial f. So let's do an example, and we'll also see how we can use some ideas about fields to simplify some of the notation that we can deal with. So let's let f be the polynomial x to the fourth plus 1 over the rationals. Now we want to find a splitting field for f. So we can do this in steps. We can also sometimes we're able to jump right to the end and see, okay, if we move up to the complex numbers, this will factor in such and such a way. And if you do that, that's fine. You can move to as large a field as you like to factor the polynomial into linear factors, and then drop down to the splitting field by just taking the smallest subfield that contains all the roots. So we can also go up in steps, though. So we can notice that this polynomial f is irreducible over q, but in our adjoint x, we have that f is equal to x squared plus the square root of 2x plus 1 times x squared minus the square root of 2x plus 1. So we can factor it a little bit further if we move up to r, but we still can't split it completely. So our f still does not split in the field r. But now that we have these in a quadratic form, we can use the quadratic formula to get there. So by the quadratic formula, roots of x squared plus the square root of 2x plus 1 are given by negative square root of 2 plus or minus the square root of negative 2 over 2, which is negative square root of 2 over 2 plus or minus the square root of 2 over 2i. And similarly, roots of x squared minus the square root of 2x plus 1 are given by the square root of 2 over 2 plus or minus the square root of 2 over 2i. So that means that a splitting field, and any splitting field of f, is isomorphic to q of negative square root of 2 over 2 plus the square root of 2 over 2i, and I'm going to need more room here. Negative square root of 2 over 2 minus the square root of 2 over 2i, the square root of 2 over 2 plus the square root of 2 over 2i, and the square root of 2 over 2 minus the square root of 2 over 2i. Now this is technically correct, but usually we will want to find a more efficient way of writing down the splitting fields, and generally that means simplifying and reducing the number of generators that we have here. Pardon me. Sorry about that. We have the splitting field here, but we've got a lot of redundant information. So for instance, we could say since fields are closed, under multiplication by -1. We don't need the first generator here because it's just the negative of the last one. So we don't need both of these because they're just equal after multiplying by -1. And similarly for the second and third ones, these are just equal after multiplying by -1. And so our field, our splitting field, can be more simply written as q of square root of 2 over 2 plus the square root of 2 over 2i, and the square root of 2 over 2 minus the square root of 2 over 2i. We can do even better, though. We can note that fields are closed under division and multiplication by 2. So we have that the field could be described as q of the square root of 2 plus the square root of 2i and the square root of 2 minus the square root of 2i. Now, this field is clearly contained in the field, the smallest field containing both q, or containing q and the square root of 2 and I. However, it turns out that these two are equal, and the easiest way to do that is to show that you can get the square root of 2 and I out of these two generators. So notice that to get the square root of 2, we could take the square root of 2 plus the square root of 2i plus the square root of 2 minus the square root of 2i. That'll give us 2 times the square root of 2, and if we multiply by 1/2, then we get just the square root of 2. And similarly, I is equal to 1 over, if we take the square root of 2 plus the square root of 2i minus the square root of 2 minus the square root of 2i, we get 2 times the square root of 2i. And so we can divide that by 1 over 2 square root of 2. And you say, well, wait, can we divide by the square root of 2? Well, yeah, if we're considering the smallest field, which contains the square root of 2 anyway, then we certainly can. We already know that we can get the square root of 2. So we know that the smallest field containing both of these generators is one in which we can divide by the square root of 2. So in fact, we can say not just contains, but these two are equal to one another. So this would be the simplest, or one of the simplest ways that we can write down the splitting field for the polynomial x to the 4th plus 1 over the rational numbers.